Thanks, Rebecca. My name is Vaco Allen. I'll be kind of emceeing here a little bit, and you'll hear from me in the presentation as well. And you'll see all the faces that are disappearing right now later coming up too. So welcome aboard. Thanks for joining us here for the next roughly hour or so. We're going to talk about the fundamentals of stormwater treatment. But before we do, I just want to mention a couple things. One is, if you'd like copies of these slides after the fact, look in the chat. We're going to put the email address of David Core there, so that you can email him and say you'd like a copy and we'll send it to you. The other thing is that you can use the chat for questions. So we would love to have your questions as we're going through. If we forgot to spell out an acronym, or you have any deeper question about what we're talking about, please put that in the chat. And at the end, we should have ample time to go back and look at all those questions and hopefully give you some live feedback. And the last thing I want to just mention is that we're going to be talking really about stormwater treatment here. If you know Contech well, you may know that we have lots of other things to offer, like infiltration, rainwater harvesting, detention, as well as bridges and pipes and all kinds of other things. So we're going to just focus on stormwater treatment here, and just want to note that, because if you do have questions about the other stuff that I'm not covering here, that we're not covering, just reach out to your friendly neighborhood Contech rep, and we will definitely hook you up with whatever information you're desiring. So without further ado, I'm going to figure out how to advance the slides here, and we will get started. Oh, there we go. We'll too fast. So my name is Vaco Allen. I'm the regulatory director here at Contech. I'm joined by Marko Popovic, who is the separation product manager, and Tamer Mammon, who is the filtration product manager, and Dan Dodson, who is our biofiltration product manager. And we'll all have starring roles in the presentation here today as we go. So here's a look at our agenda. We'll start off on the regulatory side. So that's me. I'd like to just start with the Clean Water Act, because that's really what gives us the direction that we follow for all of our land development projects. And the Clean Water Act has been around for a long time, about 50 years actually. Started really focusing on industrial point sources and on the discharge of public sewer systems. So those treatment plants and those industrial sources were really the main sources of pollution in our nation's waters at the time. And as we made progress to clean up those sources, we realized quickly that there was a lot of other pollution that was entering our receiving waters. And so the Clean Water Act was amended in 1987 to create the municipal stormwater program, as well as industrial and construction, under the NPDES, or National Pollutant Discharge Elimination System permits. The objectives for the Clean Water Act as a whole and all those different permitting approaches are really the same. Our intent is to protect and restore the beneficial uses of the waters of the United States. You may have heard WOTUS in the news lately. Won't get into that, but that's what we're trying to do here. And the way that we do that is to reduce the discharge of pollutants of concern to the maximum extent practicable. It's a little bit of a word salad, kind of legalese language, but you'll see that language really in every stormwater permit. And the MEP, or maximum extent practicable directive, is really an intentionally vague or flexible standard. It intends that we would all be designing and implementing the most effective controls that are also technically feasible and not cost prohibitive. So what does that actually mean? Well, the answer to that question really depends on where you are literally, because it's often the local regulations, or in many cases, most cases, it's the local city or county that you're going through to get your stormwater permit on an individual project. And that's where the rules that we must follow are most clearly spelled out. So we're going to talk specifically about municipal stormwater permits. Those are the permits that really regulate post-construction runoff control, among other things. And it's important to note that these permits, the NPDES permits, are issued usually at the state level, and sometimes for phase ones at a city or urban area level instead. So in either case, whether you're a phase one with a population of greater than 100,000 people, or a phase two where you're smaller but still in an urban area, the NPDES permits basically regulate those MS4 operators, so the owners and operators of the municipal separate storm sewer systems. And they require them to do a lot of things, including having a post-construction runoff control program. And that's really what gives us our requirements for land development projects. So typically you'll have a state level if it's phase 2 or a urban area phase 1 permit. And in that permit, it'll have some post-construction runoff control requirements. And the permittees, those people who are regulated, or I shouldn't say people, the agencies or jurisdictions that are regulated by the NPDES permit, they will extend those requirements to land developers through a post-construction runoff program, or sometimes called a land development program. And this really happens at the local level, and the requirements vary widely. One thing to note here, just with the map, is that when you look at all the phase 1 and phase 2 jurisdictions, there's between 6,000 and 7,000 of them across the country, and they pretty much exactly line up with where the locus of population is. So in other words, these are really designed to get at urban land uses and contributions to receiving waters of pollutants by urban development. So we're going to kind of go through a continuum here of stringency of regulations, starting with the least stringent, what I call the Wild West, not necessarily in the West, but oftentimes it is in the West. And there are 7 states that have specific state level statutes that say we can't go beyond the Clean Water Act. So if there's no there's no design storm in the Clean Water Act, we're not going to have one in our permit. If there's no specific pollutant removal standards, we're not going to have any in our permit either. A great example of that is Texas, where at the state level, their phase 2 permit, it really just requires a program that will force land developers to have sites that install, implement, or maintain a combination of structural and non-structural BMPs that are appropriate for the community and that protect water quality. Now, if you're a designer and you come across that language, what does that even mean? There's nothing really specifically actionable or measurable or quantifiable there, but that is as far as they can go in Texas at the state level, because they have a state level statute that prevents them from being more specific. In some local areas within Texas, it's a little bit different. Like, for example, the Edwards Aquifer Zone, where they have very specific sediment removal goals and actually have an infiltration prohibition to keep from potentially contaminating the Edwards Aquifer, which is an important water supply feature in the region. So those 7 states listed there, you're not going to find much in the state level requirements, but there may be something at the local level, hopefully. And there's about 10 other states that have very similar statutes that say that they must be consistent with the Clean Water Act, and that's often interpreted as not having permission to go beyond with regulations. This probably sounds very foreign to those of us in California, Washington, along the East Coast as well, that have very, very stringent standards. So in these kinds of Wild West situations, a lot of times stormwater standards are just kind of tacked on to what they might have for flood control. And in some cases, you can just put in a trash rack like the ones shown here in the picture. And sometimes that's good enough for stormwater quality, at least from a local regulatory perspective. Maybe not good enough in terms of having an actual measurable impact downstream. The next step up, if something is regulated, it's typically going to be sediment. And sediment is important to control because it has great impacts on receiving waters. All those benthic organisms, those ones that live on the bottom of streams, rivers, lakes, etc., they can literally be smothered, both the plants and the animals. So it can really change habitat and just inundate downstream areas, especially when runoff from construction is allowed to go unchecked. So we have some standards for sediment. And some treatment technologies, which we'll talk about later. The 2 primary ways that remove sediment are through gravitational separation, which is, think about like ponds, or we'll talk about hydrodynamic separators, or filtration. So if you have a 80%, or if you have a TSS standard, it's probably 80% removal. And you may wonder, why do we have that anyway? Look, who came up with that and why? Well, when the Clean Water Act amendments for stormwater were created and we had this MEP language, the EPA was not any more specific than that in terms of requiring certain levels of control. However, a couple of years later, the CZRA, or the Coastal Zone Reauthorization Amendments, came out, and in those amendments, they identified this 80% TSS removal goal as an example of a standard. And since there was no other better thing that had come out of EPA at the time, people grabbed that. A lot of programs continue to run with that standard to this day. And it actually does make some sense. That's about the level of treatment that you could probably expect from some of the conventional systems that were used at the time, like wetlands and wet ponds, and say sand filters. And there was an expectation that if you removed 80% of TSS, then you would also be able to remove some amount of the metals and phosphorus and other pollutants that are associated with solids. So that's stuck. So in a lot of places, we do have this 80% TSS removal standard still. So it's important to talk about what that actually means. Like, what is TSS? And the answer is it's determined by the analytical method that we use to measure it. Essentially, you take a bottle and you sweep it through a flowing stormwater, and you take that bottle and you either stir it up or shake it up, and then you pipe that out or pour out a portion of that sample through a filter paper, and whatever is filtered on that paper is the TSS load, and then you calculate your concentration from there. Works great, and it's a good characterization of stuff that's actually suspended in stormwater. Turns out there's a lot more stuff that's in stormwater, particularly the bed load stuff. We're talking about sand and stuff that's bumping along the bottom and won't necessarily make it out of the bottle in that kind of a test. So back about the year 2000, the USGS developed a companion or an additional sediment measuring standard called SSC, or suspended solids concentration. And the only difference there really is that instead of taking a subsample out of the bottle, you just filter the whole thing. You filter all the water in the bottle and you capture all the solids there. So it's a much more complete measure, and it actually captures the sand fraction. So from EPA's perspective, when they were talking about TSS removal, they were really looking at that silt and clay fraction, what you see shaded on the table here. They weren't so much interested in the sand fraction, but that actually is important. So it's also important when we're looking at TSS removal standards to know whether we're specifically talking about TSS or SSC or some combination. So if you've been thinking that this is all a little abstract so far, here's a handy visual for you to help us visualize what these different particle sizes actually look like. So there's a human hair draped across the top. Depending on how thick or fine your hair is, maybe that's somewhere between, say, 100 and 200 microns. You see beach sand, fine beach sand there. A grain of salt is in the 60 micron or so. So really, that's actually around the dividing line between what is likely to be considered TSS and what is basically fine sand and coarser or finer. So finer materials, looking down in the 7 to 10 micron range, we're talking about dust particles and red blood cells. So these are very small, much smaller than you could see with the naked eye. Hopefully that's a good visual orientation to what we're talking about here. So when it comes to TSS standards, it's more important, or it is important to have more as part of your standard than just 80% or some numeric target. We have to have that particle size distribution or range. Like, are we talking about SSC or TSS or some specific target particle size? Having that removal efficiency target of 80% or something else, or an effluent concentration, is important. And third thing we need to know is, are we trying to do this on an annual basis? Are we trying to do it during a specific design storm? Are we trying to do it on average across all flows that come through? So it's important to articulate all those three things because they will all impact the sizing of a treatment system. And whenever we get these standards all together and we're looking at potential options, one thing that's always important to focus on is performance verification. Like, how do we know that whatever treatment systems that we're looking at, whether they're proprietary or non-proprietary, how do we know that they're going to actually meet whatever performance standards there are out there? So we're going to talk briefly about two different programs here, one in New Jersey and one in Washington, that get at this performance verification question. But before we do, I just want to mention two other resources. And by the way, at the end of the presentation, there will be a resource slide that has more complete links for ASTM, BMP database, New Jersey, and Washington. So you don't have to jot it down now. So ASTM has a new committee called E64. It's a committee on stormwater control measures. We're actively creating standards for both public domain and proprietary stormwater systems, for media filters, hydrodynamic separators, and other systems that standardize the way that we look at these systems and how we measure their performance in a comparable way. There's also the International BMP database. This is a great repository of hundreds of field studies that have been conducted on various stormwater systems. So you can look, for example, if you want to look at bioretention and see how well it does for zinc or for phosphorus, or look at sand filters and see how they do on average for bacteria. It can give you all those kinds of pollutant and BMP combinations. Very handy. So let's dive into New Jersey for just a second. Maybe we have some New Jersey people on the call. This is a laboratory-based protocol that's really designed to produce very repeatable, very high precision data using a manufactured silica product. So this is a sediment surrogate, really, that's made of silica, the primary component in sand and glass, that is all these little beads that are from about 1 or 2 microns all the way up to about 1,000 microns. So you can see from the chart here that the average particle diameter is about 75 microns. And they have different standards and protocols for hydrodynamic separators and for filters. For HDS systems, the target is to get to 50% removal, which means that you need to remove particles in the range of about 75 microns and coarser. For filters, the target is 80% removal, which means that we need to be removing particles that are about 8 microns and coarser. So those are two very different levels of performance and 2 different types of technologies to get there. Assuming that you do your testing following the protocol and you can collect enough data to write a report, you submit that report to NJCAT, the New Jersey Corporation for Advanced Technology. They will verify that, yes, you did, in fact, hopefully, complete the testing following the protocol and that you've disclosed or included enough information in your report to be useful and to really fully describe your experiment and all the results. With that NJCAT verification report, New Jersey DEP will review it, compare the results to their performance standards, and they will issue a certification report at the end of the process. So there are many states and local programs that reference the New Jersey DEP certification as an acceptable standard in their local area, often for pretreatment and sometimes for standalone treatment. So let's see. So we have a picture here of a testing laboratory. This is actually the the Contech laboratory. And I just have this here to remind myself to tell you that there's a lot of things that happen in the field that don't happen in a laboratory. Laboratories are great for precision and repeatability, but things like freezing weather or rain on snow events or bud shatter or leaves falling or intense storms or all the different kinds of things that you can have happening in a watershed, they don't really get measured in a laboratory. So it's really important to go out into the field and to do performance verification there as well. So that brings us to the Washington program, which is all about field evaluation. And you have to go, as part of the program here, following the TAPE protocol, you have to measure at least 15 storms out in the field and collect enough data so that the Washington Department of Ecology can make an assessment as to whether your technology meets certain performance standards or not. And here are the performance standards. For TSS, they want to see at least 80% TSS removal for influent concentrations greater than 100 milligrams per liter. If it's below, you need to maintain an effluent concentration of 20 milligrams per liter or less. And they have other standards for dissolved metals, for phosphorus treatment, 50% phosphorus treatment. They have an oil treatment standard, but that's typically more for industrial situations where you have more than 10 milligrams per liter coming in. And they have a pretreatment standard, which is really where hydrodynamic separators fit, which is about 80% TSS removal that they're requiring. So the idea here is you go out into the field, you collect a bunch of data, you submit that to ecology. They send that data out to a board of external reviewers who review your data with a very fine-tooth comb and make sure that it all conforms to the protocol and meets these standards. And if you get to the end of that process, you can get a general use level designation, which includes some information about the technology, as well as any limitations of use and important design requirements, like what hydraulic loading rate you're allowed to use and those sorts of factors. Again, this is a program that's used widely throughout the country, not just in Washington. So moving beyond TSS here, if there's something else regulated, it's probably nutrients. There's about a dozen states that have a phosphorus standard. Phosphorus tends to be the limiting nutrient in freshwater ecosystems. Nitrogen tends to be the most limiting nutrient in marine waters. When you have too much of either of these pollutants or both, you can have algae blooms. And then when the algae dies, then it goes down to the bottom and all the microbial activity digests it, and the dissolved oxygen levels get depressed, and then fish die, and it's just a bad scene. So to try to get around having these kinds of eutrophication impacts, we try to keep our phosphorus levels lower in stormwater than they would be without controls. You can get to maybe 40, 50% phosphorus removal with a system that's getting 80% TSS, and you can maybe get 20% nitrogen removal with such a system, but oftentimes we need more than that. So in the case of phosphorus, we're going to be using active media that has absorption capability for phosphorus. And with nitrogen, it's really hard to get much more removal unless you have like a wetland or something that has an oxic and an anoxic zone, where you can have these microbially mediated processes that are required really to remove more nitrogen. Wrapping up here my section with a couple more slides. You all may have, I'm sure you've heard the term by now, of green infrastructure or low impact development. There's been a pivot, especially pushed by EPA in the last few years, to update permits to include low impact development or green infrastructure requirements. This is great because it requires us to slow it down, spread it out, sink it in, basically do the opposite of what we had been doing for many, many years, which is to channelize everything and drain sites as quickly as possible and get that water away from everything that we built so it doesn't cause problems. However, oftentimes LID or green infrastructure regulatory frameworks are really kind of vague when it comes to treatment. Often there's an assumption that if you do things like we see in the illustration here, just put in a system like this, as long as it removes enough stormwater by infiltration, it's going to be fine in terms of effluent quality. A lot of times that's the case, but a lot of times it's not quite the case, especially if you have marginal infiltration capability in your soils and you're using mixes for your bioretention or rain gardens that contain a lot of compost or other materials that have a lot of nutrients in them that can be mobilized downstream. So ideally, if there are LID or green infrastructure requirements, they are also accompanied with some specific performance targets, either in terms of pollutant removal or runoff reduction. Instead, sometimes we see things like, reduce your directly connected impervious areas or reduce your runoff by certain percentages. It can be hard to know exactly what kind of treatment system to design in a situation like this. But typically, they are landscape based, and we'll see with our bioretention systems, you can get a lot of great work done from a pollutant removal perspective with LID or green infrastructure technologies. And the last slide for me here is I just want to talk about municipal retrofit projects. These are becoming more and more common as jurisdictions are trying to deal with legacy impacts of urban development. Essentially, they're going out and retrofitting part of their urban areas to include regional facilities that capture runoff from areas that were built usually before stormwater management was a thing. So the reason I bring this up is it's important because these projects are typically not going through the land development review and approval process. So those 80% TSS or whatever it is goals that you have locally may not apply to these projects. A lot of times we're taking whatever available land there is and doing the best that we can, doing the most pollution removal or infiltration that we can in these projects. And you're given flexibility and freedom, usually as a designer here, to do the best you can and not be bound by specific performance removal targets. The illustration here is of a Filterra system at Manchester Stormwater Park in Washington, where we treat about 100 acres of upstream area through these individual bioretention cells prior to the water going out to Puget Sound. So it's important to note that there are these kinds of projects out there that don't really necessarily follow the land development rules. So with that, we're going to move to the next section of the agenda, and I'll turn it over to Marco. Thank you.
Thank you, Vaco. So we're going to move into the first of our three treatment categories, that is hydrodynamic separation, which you will oftentimes hear us call HDS. So bear with me as I use a number of acronyms. I will try to elaborate on what each of those stands for. Hydrodynamic separators are based on three fundamentals: swirl concentration, flow controls, and gravity separation, which we'll refer to for the purposes of this conversation as sedimentation. So getting into what each of those actually looks like, we have a graphic here on the right-hand side that illustrates this is a manhole or vault. It has several internal components, and each of those internal components plays a key feature in manipulating the way water will flow through one of these structures. This one better illustrates what that actually means. How does it take water and separate the solids that are in that water? On the top right hand side, you can see the swirl path that's created from that inlet splitter, and that ultimately elongates the flow path, which increases settling time for those particles. Therefore, we're able to capture more within a given unit. The controls themselves, while it's important that we capture everything, it's equally as important to make sure we're retaining everything that's captured in those 10-year, 100-year storm events. So when we see what we would refer to as a peak bypass event, the water on the bottom right-hand side is not going to necessarily follow the same path in low flow as it will in a typical flow, as it would with a high flow. Those flow controls, that center baffle there, will allow water to bypass without creating turbulent forces in the sump, therefore resuspending solids and discharging back into the effluent there. So I mentioned gravity separation. We'll refer to that as sedimentation. Sedimentation, for the purposes of stormwater, is the separation of solids from water by the force of gravity. We characterize this with Stokes' law here, and it's important to note, you don't necessarily need to know this equation in and out, but the particle size diameter is highlighted here to show that when we go larger with particles and we're trying to get those suspended particles out of that water and get them settled, it's obviously in a big particle going to settle much quicker. So larger diameter equals higher settling velocity, which therefore means shorter settling time. This chart illustrates that a little bit better because you can kind of see how in the case of New Jersey DEP, which Vaco talked a little bit about, he separated filters and hydrodynamic separators to say filters are going after some of these smaller particles, the silty, and hydrodynamic separators are going for sand, larger particles. Tamara will obviously talk a little bit more about filters here. The key note and takeaway from this slide would be the graph shown on the right hand illustrates New Jersey having we have PSD noted here, particle size distribution. It's looking at some of the small, but really that removal efficiency, we see that at these larger sand type coarser particle sizes. The picture on the left-hand side, and I have a couple of the bottles, but in the interest of time here, I'm not going to show it. Really what that means, and kind of further illustrates this, if you shook up those two bottles, the two on the top, you can see the particles are floating in the water there. When we let that sit for 30 seconds, that OK110 gradation on the left-hand side, which is primarily composed of sand coarser particles, will settle out a lot quicker than that of the NJDEP gradation because there's a lot more fines in there. Again, for back to Stokes' law, it's going to sit for longer in that water. Sedimentation isn't a concept that's unique to manufactured treatment devices. Sure, Contech's here telling you about the technologies that we manufacture, why we do what we do, but ultimately this is a concept that we see in detention and retention ponds. Water settles in these ponds, the large particles and small particles over a certain period of time will settle out. The reason a hydrodynamic separator is viable and used is land, available space. We ultimately don't have a lot of space in urban areas. So consolidating it, paving parking spots, putting buildings, whatever else you may need, it helps us take the forebay from a pond and put it within a separator and get that actual treatment component of the water quality attributed in a smaller footprint there. Then you talk about, it might not fully replace the pond, but if you can replace that forebay and get some sort of sedimentation within the separator, it does make maintenance a lot easier. These units, these ponds, everything has maintenance associated with it. If we're constantly capturing all the sediment that's coming in through the influent and we don't actually remove it from the structure that's capturing it, ultimately it will resuspend and discharge. Whereas with a pond, you're going to have to dredge that out. It's a pretty involved maintenance process. With a hydrodynamic separator, takes a simple vector chuck, pop the manhole lid, vector that out, and it's good to operate for future use. So we talked a lot about sediment. Vaco talked about the varying degrees of sediment that we see with larger and finer particle sizes. HDS isn't necessarily limited to that. We can add baffles, screens to target hydrocarbons, floatables, and with the screens we can look at debris and trash. So it does most of these technologies have the ability to act as a all-in-one device, again, further reducing what you're going to see on a given site. So we talked about the what. What are we looking for? What are we trying to get out of this? Now, how do we actually select one of these? There's quite a bit in the first 20 minutes that we talked about here, and it can be a bit overwhelming. I think the key takeaway here, if I were to highlight one thing, would be these treatment requirements. Flow rates. How much is actually running off into one of our units, and how much do we need to bypass? Particle size distribution, again, illustrated by Stokes' law and those graphs. It's looking at a 250 micron size isn't the same as looking at 75 micron. And then finally, that will translate to this percent RE, removal efficiency. We can't say it's going to take 50% of one particle size and then make that equal to a smaller particle size, because reality, as that chart showed, is it's not going to capture all of that. The other two considerations to have here would be trash retention requirements. Do we need to make sure all floatables, anything larger than 5 millimeters, is captured and retained within the structure? And then ultimately, does that treatment technology have the ability to bypass internally, or do we need to move that offline? One takeaway that I would ask everyone has here while I move to the next slide is, keep in mind, there's 4 structures here. When I move to this next slide, you can kind of see the ability of a single hydrodynamic separator to consolidate some of those structures. Again, these additional considerations, we figured out what size unit we need. Can we keep that online and eliminate a bypass structure? Is there a graded inlet structure upstream of that? Can we consolidate that into the separator itself? Do we have vertical space limitations, which may force us to use something like a vault in a shallower footprint? And then vice versa with horizontal space limitations, pushing us back to a manhole versus a vault. Wrapping it up here, there's quite a bit of technologies out there in the marketplace right now. Contech alone has 6 of those. Key takeaway I would say is, don't think you need to be the expert as a municipality, as a design engineer, as a consulting firm. The big thing is Contech has local representatives with all the regulatory factors in mind that Vaco discussed, as well as particle size distribution, removal efficiencies. We will steer you in the right direction to the best technology based on your regulatory parameters and your geographic parameters. With that, I will hand it over to Tamara to talk a little bit more about filtration.
Tamara, looks like you're muted.
Thank you. Can you guys hear me now?
Yes, we can.
Awesome. Hi, everybody. Today we're going to be discussing the fundamentals of filtration in my section. So we're going to start off by discussing the different pollutant removal mechanisms available through the filtration process. The most basic would be your physical removal of filtration. So this is when a pollutant particle physically impacts with the filtration medium and is removed from the stormwater. To make things a little bit more complex, we can get into our physical chemical processes like absorption and adsorption. On the right-hand side of the screen, image A is an example of absorption. So the pollutants are being physically absorbed into the filtration medium. Image B is a good example of adsorption. So this is where the pollutants are adhering to the outside of the filtration medium. One example of this is removing phosphorus in the form of phosphates. And if you can just think of or remember this takeaway, absorption involves absorbing, adsorption involves adhering. It'll be a really good place when you hear these terms in the future. You can also remove dissolved metals through cation exchange reactions within the filtration systems. Now, after the storm subsides, if there is a plant within your filtration system, which is biofiltration, and Dan will touch on this later, microbes and other organisms are located predominantly in that root zone. So the root zone provides these organisms with a permanent organic food source and a shelter. In exchange, these organisms break down the captured pollutants into soluble forms that the plant can then uptake. Once the plant uptakes these pollutants, it renews that the media and leaves that site open for the next storm event. There are multiple different sizing methodologies when you're designing a filtration system. I'd say one of the more common methodologies is a flow-based sizing approach, which requires the filtration medium to treat the peak water quality flow. Typically, flow-based sizing will result in the largest size filtration system. It can either be standalone or when paired with detention, it is most commonly upstream of the detention system, serving as a pretreatment and reducing the maintenance interval of that downstream detention. Second most common approach would be a mass-based sizing. It requires a filtration medium to remove the annual mass load received from a drainage area. Unlike flow-based sizing, this is going to result in the smallest size filtration system, and it is almost always placed downstream of a detention system. And finally, a little less common is the volume-based sizing approach. It is still used in some locations on the East Coast, like Maryland, but this requires a particular volume to be treated by filters. Sorry, excuse me. And this is also checked against a mass-based design because we want to make sure that that filtration medium isn't being inundated with sediment. On the right-hand side of the screen, you're going to see an example of how Contech would address a volume-based sizing approach. There are multiple precast sections in the storm filter box culvert. As those precast sections are butted up together, it forms your precast detention. And within that precast detention, we will have an underdrain and a few storm filter cartridges, which will help you to meet your treatment requirements. Now, another important criteria in addition to sizing is what filtration medium do you want to pursue? Traditionally or conventional systems, you may have a sand filter or a bioretention system. These have a sand or a soil-based media. Typically, the engineer of record will specify and design these systems, and then the contractor will source and install them on site. As you can see from the pictures, they are at grade. Sand filters don't always need to be at grade. Sometimes they are below, but it is a top-down flow path of the water for the filtration. When you get into a manufactured filter, the flow paths are slightly different and you get a more efficient system, which we will get into the benefits of a little bit later. So how do you know when to use all of these different options? If you're looking at a conventional system, like a sand filter, I'm going to focus on sand filters and conventional. Dan will talk about bioretention in the next section. As I mentioned, sand filters and membrane offerings will primarily target sediment, trash, and floatables. Now, this isn't to say that they can't remove nutrients or metals. They're just more efficient at removing particulate-bound nutrients and metals. If you're looking to remove more dissolved nutrients and metals, that's when you would start looking at a media filter. So similar to a membrane or sand filter, it can target that sediment, trash, and floatables, but can also target specific pollutants of concern by actually changing the media within the cartridge. That change in composition can target different nutrients and metals you're looking to remove. What are the benefits of using a proprietary filtration system like a media or membrane system versus a conventional? Vaco touched on it earlier and explained it very well. Their proprietary BMP's best management practices are held to a high standard. They have to go through quite a bit of testing in order to get their approvals, and that data has been repeatable and proven. With conventional systems, there are plenty of studies out there you can reference, but they don't have to go through that same approval process as proprietary systems do. The next benefit is the quality assurance and control of our media. As I touched on previously, the engineer of record will design and spec the system. It is then up to the contractor in a conventional system to source the components and install them. When you're sourcing components locally, there will be some variance in the composition, which will lead to varying performance results in the field. There's also a risk of media contamination, because if these medias are being blended on site, there could be a mix of construction runoff or sediment that gets in the media, leading to a need for some premature maintenance. When you have a proprietary system, as a manufacturer, we know where we are getting our medias from and that they meet a specific spec. We also have a safe location to blend them and keep them clean. They're then shipped as a pre-packaged system to your site, where we'll have specific activation rules to keep those cartridges protected until the site is fully stabilized. Third benefit would be an integrated bypass capacity. Usually with conventional systems, you will need an additional structure up or downstream to convey your bypass flows. In the jellyfish peak diversion image on the right, you will see a baffle wall and a weir wall system integrated within the system already. So no need for an additional structure, which can save on installation and material costs. The top-down flow path of a conventional system typically leads it to have a larger system footprint. When you are looking at a proprietary cartridge system, like a jellyfish or a storm filter, these accept a radial flow, so there's more surface area for the water to come in contact with, leading to a more efficient system footprint. Another benefit of these systems is they're almost always installed underground, which leaves ample space for the owner to use at grade and profit off of. As a manufacturer, we typically will always have design through installation support, cradle to grave for a project, and proprietary devices offer significant maintenance cost savings, which Dan will touch on at the end of the presentation. So what do we need to help you size a filter system? We're going to want to know your pollutants of concern, because that will help us determine what filtration medium is best suited to your site. We will also want to know your project location. So that way we're aware if we have to meet any Washington or New Jersey approvals and follow and adhere to those sizing approaches. If you're doing a flow-based sizing approach, we'll want to know your treatment and bypass flow rates. Now, different localities will use mass-based or volume-based sizing approaches. In that instance, like Marco said, the stormwater consultant or your local contact is going to help guide you and tell you what information we need to give you the best proposal. Finally, we would like to know your available drop from inlet to outlet invert. The more drop you have from inlet to outlet invert, the taller the cartridge you can use. And when you can use a taller cartridge, you can use fewer of them, which will shrink your system footprint. We do have options for low drop, but typically if you have a shorter cartridge, you need more of them and your system will grow a little bit in size. And I did want to note that Contech stormwater filtration devices are not offered in applications where industrial general permits are met. I know some of the content in this conference is covering industrial applications, and that unfortunately is just not a field that our stormwater devices play in. So what happens if we give a proposal for a filter and it doesn't quite meet all your site constraints? There's no need to worry. We have a very wide filtration portfolio that we can leverage to help you meet your site's needs. Our media filter offering is going to be the stormwater management storm filter. We have various different medias and testing data for those. And currently there are 2 general use level designations for the storm filter system and 1 New Jersey certification. Our jellyfish filter is a membrane filter that has a deeper sump. This has Washington general use level designation for basic and phosphorus treatment. And finally, we have the high capacity Kraken filter as an offering in New Jersey with NJDEP certification. And now I'll hand things over to Dan so that he can finish off the presentation talking about the fundamentals of biofiltration.
Thanks, Tamara. To wrap things up, we're gonna dive into the biofiltration side of things. As soon as I get this working, there we go. So as Vaco and Tamara mentioned earlier, regulations may require low impact development or LID, or have those additional removal requirements such as trash, metals, nutrients. When these removal requirements or LID are required, a biofiltration or bioretention system is kind of the solution that you're going to be looking for at that. So let's start by defining biofiltration. What is it exactly? A biofiltration system is a pollutant control mechanism that incorporates physical and biological processes via vegetation and soil organisms that's going to capture, immobilize, and treat your harmful pollutants. And these systems, they come in a variety of different formats, from your conventional systems such as bioswales, rain gardens that you see on the left-hand side of the screen, to your high-rate biofiltration systems that are shown on the right-hand side. So let's dive in. Let's compare these types of systems. What are they? When do we use them? And how they can fit into your project. And so first off, let's just start with the conventional systems. These are ones that I'm sure most of you have seen or used on a project in the past. Conventional systems are those ponds, swales, rain gardens. They utilize a media that's typically specified by the local agency for treating the stormwater. And the media that you use in these, it'll get you a flow rate of about 1 to 12 inches per hour, or approximately 0.1 GPM per square foot. Now, I want you guys to key in on that 0.1 GPM per square foot number. You're going to want to remember that as we kind of move through the rest of the biofiltration slides. You'll see how it kind of differs with the different options. But to continue with the conventional systems, they can be anywhere up to 10% of your impervious drainage area. So they do take up a decent amount of space. They also, the full system, including your mulch, your soil, your stone, piping, plants, all of that's got to be designed by the engineer. And on top of that, everything has to be locally sourced, installed by the contractor, and then maintenance ultimately ends up falling on a landscape crew. And we'll get into maintenance a little bit at the end. So it just kind of shows you all the different parts and pieces that you need within a conventional system. So, all right, everyone's still got that 0.1 number in their head. As we move on to the alternative to the conventional, that's your high-rate biofiltration systems. And right off the bat, you'll notice the difference in the flow rates. Why else would they be called high-rate biofiltration systems? So with these systems, the engineered media, it's fully pre-engineered. It gets flow rates between 1 to 3 GPM per square foot. So that's an order of magnitude times what you're going to see in the conventional systems. So this is just going to result in a benefit of reducing your footprint needed, and therefore it's going to open up the usable area that you've got on a job site. So there's more, as you can read here, there's more advantages than just your increased flow rates. The first of which is the testing that these go through. Tamara kind of keyed on that with the filtration systems. Same thing goes for the high-rate biofiltration systems. They go through both the laboratory and field testing through New Jersey and Washington, and they're identified through the international BMP database that Vaco mentioned. This kind of gives you that specific data that can be referenced as to how they perform, whereas kind of the locally sourced medias and blends may have some varying performances. You couple the high flow rates with the verified test data, add in that each of these systems is a fully packaged design. So that's easy installation, maintenance guidelines, quality control. You've kind of got yourself a full-fledged biofiltration system that you need, just in a much smaller footprint. So the next question that we typically get asked is, when can I use these high rate biofiltration, and where can I use them? And of course, you can use them in replacement of the conventional bioretention systems. You just utilize a smaller footprint due to the higher flow rates, but there are other applications that you might not be aware of. The first is the decentralized system, where you kind of have those smaller systems that are scattered throughout the job site. So the decentralized systems, they're ideal for your urban retrofits, your roadways, because you've got a shallow configuration and the ability to install them within the existing infrastructure, which is a huge benefit for those urban retrofits, public infrastructure jobs that we're constantly seeing pop up. Another use for the high rate biofiltration systems is to put them downstream of detention. Tamara mentioned earlier with the filtration portion, biofiltration can do the same thing, where we're also using it downstream of water storage, and that's just going to allow for more usable land space upstream. And it also kind of doubles down, as you can see with the picture, with the ability to incorporate infiltration into the ground through both our detention system and the biofiltration unit. And that's kind of what that picture is depicting there on the right-hand side of the screen. And finally, one other application, you heard kind of Veiko mention it at the end of his portion, is that these systems can be used in regional treatment areas. The increased capabilities with the high flow rates allow for the drastically reduced footprints for the big regional treatment systems. With the engineered media, your kind of reduction of your footprint is up to 90% versus the traditional practices, because we've got that 10 times multiplier in flow rates that we discussed in the beginning. So it kind of makes it the perfect low impact development, or LID, solution for those high volume stormwater treatment areas, while still having the ability to be planted with those native plants that kind of resemble a natural wetland, which is what you see in the picture. So you've seen it with separation, you've seen it with filtration, with biofiltration. What are some available technologies that are out there in the market that you can use? Well, at Contech, we've got a pretty robust portfolio of products that are high rate biofiltration systems. And you've actually seen examples of these in all the previous slides already. The Filterra Bioscape, that's the example of the regional detention system, where it's not built into like a precast box or anything. It's kind of open, but we utilize our pre-engineered media. The modular wetlands there in the middle, that was used in both the package design example and the downstream of detention example. And then of course our Filterra Vault, that was used for the decentralized treatment example. And all three of these systems, they've got multiple applications that they can be incorporated into, and kind of the easiest way to determine which system to use is to visit the link shown here at the bottom. It's going to take you directly to the project design tool. We can fill out some simple project info, and it'll connect you with the local Contech rep. I think Marco had said it best, is you guys don't have to be the experts in these type of treatment devices. That's why we've got engineers and regulatory managers that can help you kind of maneuver and decide what the best option is going to be. Now, there's one area that we've touched on, but we've kind of yet to focus on for all of the different systems that we've talked about, and that, of course, is the maintenance aspect. Each of us today have already touched on through the presentation whether you're dealing with separation, filtration, or biofiltration, the conventional systems have that larger footprint, particularly for filtration and biofiltration. So those larger footprints, it's going to lead to increased maintenance time, labor, the materials that are needed, which just diminishes the overall life cycle cost of the system. And on top of the increased size and cost, each system, you got the widely varying maintenance intervals and procedures, and each maintenance provider and materials, it all kind of falls on the end user to source it locally. And then also on the flip side, the manufactured treatment devices that we've talked about, such as hydrodynamic separators that Marco mentioned, the filtration devices that Tamara covered, and then the high rate biofiltration systems that I just touched on, they all have that more compact footprint. They have reduced labor, reduced material costs for maintenance. They've all got that specified maintenance procedure, certified maintenance providers, and they only require a single point of contact for replacement of any of the materials that you need. So that's just going to help lower the overall life cycle cost. And it's a huge selling point when you're talking to developers and owners, is that long-term cost. So that kind of wraps things up here. I think we're kind of right around our time frame. Want to thank you all for taking the time to listen to the fundamentals of stormwater treatment. Vaco kind of mentioned this earlier, but here you can find many of the resources that we've referenced throughout the webinar. There's a Contech website that's got a variety of helpful resources, from specifications, product design worksheets, etc. You've heard Vaco talk in depth about the different databases that kind of guide stormwater treatment, like Washington, New Jersey, International Stormwater Database. So those links are here as well. I believe this presentation will be available after the webinar is done. So everyone will have access to those links afterwards. If not, within the chat is who you can reach out to get a copy of this, and we're happy to send it out. So now we'll kind of open it up for any questions that people have. You can either just kind of shout them out, or I believe, Vaco, you're kind of the question master from the chat function. So anything that's kind of popped through, feel free to chime in.
Great. I'll just hit a couple of these that came up in the chat, and definitely if you're online, type something in if you have a question, or you can just unmute and turn your video on if you're feeling bold, want to join the party. So first question here around any of these HDS devices counting toward full capture in California. Simple answer, CDS and debris separating baffle box. Yes, both of those systems have screens in them, and the trash capture standard requires removal of particles 5 millimeter and greater. And those systems will get the job done, as will the filters and biofilters as well, because they're not going to let trash through either. Next question is that like a bioswale? I think that's probably, that came in around, Dan, when you were talking about the bioscape system. So maybe you just want to note how it's different or like a bioswale. Oh, you're muted, Dan.
I was talking to myself. Yeah, it is similar to kind of a bioswale, kind of rain garden, where we do have the different types of plants that we can integrate into it. However, it's different because it does use our own proprietary media blend that we've got, which gives you those increased infiltration rates.
Yep. Crucial part too is that it has an underdrain, and a lot of times bioswales don't have an underdrain. A lot of times they're designed as a conveyance system as much as they are a treatment system. Depending, nomenclature is different depending where you are. I see Lisa. Hi, Lisa. California question. I love those. This is kind of a granular one, so maybe I'll follow up with you afterwards. But in LA County, the question is which of the devices meets the Bio 1 standard? LA County's manual is out of date. They have a new permit and they haven't updated their manual to reflect the new permit yet. Both Filterra and modular wetlands can be designed to fit the bioretention criteria in LA. But it's kind of complicated to get there. It's got to be volume based and some other criteria. So that's the short answer. Anybody want to speak up for PFAS? Any of our systems remove PFAS? That's a hot topic. I'll just hit that one real quick. We're not really seeing much for PFAS removal requirements in the stormwater world at this point. That may come at some point. We know that we will have possibly some effect with the sorptive media filtration system. So that could be modular wetlands, Filterra, storm filter. But the other systems are not going to remove it. And at this point, it's more complicated than anything. If you do have a PFAS removal system, how do you dispose of the spent media? You know, all those questions have not been answered yet. So we're really in infancy there with that pollutant, as well as some other emerging pollutants that we just don't have a lot of data on yet.
And Vaco, we know what PFAS is, but do you want to expand on what that acronym stands for everybody else?
Per and polyfluoral aromatic, I think. I don't know what the S stands for, but someone could maybe put that in the chat. But basically, it's an additive to fireproofing foams. You know, it's in Gore-Tex. It's on nonstick pans. It's basically a chemical additive that is called a forever chemical. It sticks around in the environment for a long time and causes human health impacts. And it bioaccumulates as well. So it's nasty stuff. It's ubiquitous. Stormwater is not a major contributor as compared to wastewater and just, you know, environmental releases like firefighting foams and, you know, shedding of industrial products that have PFAS associated with them. Polyfluoroalkyl substances. Thank you.
So you're under the bus. Figured that'd help.
Great. I think those are most of the questions here. You have an email address at the beginning, all of you, if you look in the chat to get a copy of the slides. And as I said at the beginning, always feel free to reach out to your friendly local neighborhood contact rep, which you can find through our website if you don't know one of us. And look forward to seeing you there.
Fantastic. Well, thank you, Vaco and Tamara and Marco and Dan. This was awesome. We're so glad to have you part of Stormwater Awareness Week. And if you missed any part of this workshop, it has been recorded and will be up on our website in between 24 to 48 hours. We'll have it up there under 2023 recorded workshops. So you can share this with whoever you think would benefit from it, or go back and watch it yourself. But a big thank you to the Contech team, and hope you guys enjoy the rest of Stormwater Awareness Week. We hope to see you at some of our other workshops.
Great. Thank you.
Thank you.